You think you understand motion. You don't. Everything you were taught about why things move, why they stop, why they keep going, it's all backwards. Not wrong exactly, but backwards. And Richard Feynman knew this. He spent his entire career trying to get people to see it. To really see it. So let me show you what he saw. Here's a question. Why does a ball keep rolling after you let go of it? Think about it. You push a ball, you release it. It keeps moving. Why? Your teacher probably told you it's because of inertia. Objects in motion stay in motion. Newton's first law. You memorized it. You repeated it on tests. But that's not an explanation. That's just a label. That's just giving the phenomenon a name and pretending you understand it. Feynman would stop you right there. He'd ask, but why does it stay in motion? What makes it keep going? And you'd probably say, because nothing is stopping it. And he'd say, okay, but why should that make it keep going? Why shouldn't it just stop naturally? See the problem? We're so used to the idea of inertia that we forget how absolutely bizarre it is. There's no reason, no obvious reason, why an object should remember that it was moving and continue moving. None at all. Let me put it differently. Imagine you've never seen motion before. You're trying to predict how things behave. Someone pushes a ball and lets go. What should happen? Well, the push stops. The force ends. So naturally, the motion should end too, right? That's the intuitive answer. That's what makes sense. The ball should stop as soon as you stop pushing it. But it doesn't. The ball keeps rolling. And this is deeply, fundamentally weird. Motion persists without a cause. Once started, it continues on its own. That's not obvious. That's not natural. That's one of the strangest facts about our universe. Now, here's where the lying comes in. Because your physics teacher told you about friction, told you that objects do stop, eventually because of friction. Take away the friction, and they'd keep going forever. So friction is what stops things, and without friction, motion is eternal. Okay, fine, but that just pushes the question back. Why does friction stop things? What is friction doing that removes motion? And more importantly, why doesn't friction exist in the first place? Why do we need to remove it to see natural motion? Isn't friction natural too? Here's the truth Feynman understood. The question is backwards. We shouldn't be asking why things keep moving. We should be asking why they ever stop. Because stopping, slowing down, that's what requires explanation, not the continuation of motion. Let me show you what I mean. Think about the universe at its most fundamental level. Particles, atoms, the basic building blocks of matter. Do they experience friction? No. Not in empty space. A particle moving through a vacuum just keeps going, forever. No slowing down, no stopping. Eternal motion. So motion doesn't need a cause to continue. Motion is the default state. It's stopping that needs a cause. And what causes stopping? Interactions, collisions, one thing bumping into another, that's it. That's the only way motion changes. But we don't experience this in our daily lives. We live in a world full of air, full of surfaces, full of friction. Every motion we observe is being constantly interrupted by countless tiny collisions. The ball rolling on the ground is hitting air molecules, scraping against the surface, losing energy to heat and sound. It's being stopped by interactions. So, we developed an intuition that motion requires continuous force. Push something, it moves. Stop pushing, it stops. That makes sense in our experience, but it's wrong about the fundamental nature of reality. Feynman called this the difference between the apparent and the actual. The apparent behavior of objects in our everyday world versus the actual behavior of matter at the fundamental level. And physics is about seeing past the apparent to grasp the actual. Now, watch this. This isn't just a philosophical point. This changes everything about how we understand force and motion. Because if motion doesn't need a cause, then what does force actually do? Here's the conventional answer. Force causes motion. You apply a force, you get motion. The bigger the force, the more motion you get. Simple. Wrong. Completely wrong. Force doesn't cause motion. Force causes changes in motion. That's Newton's second law, but nobody really thinks about what it means. Force equals mass times acceleration. Acceleration. Change in velocity. Not velocity itself. Change. Let me make this concrete. You're in a car, cruising down the highway at 60 miles per hour. Are you experiencing a force? No, zero force. You're moving, but no force is acting on you. The car is coasting. The engine might be running just to overcome friction, but if we ignore friction, which we should for understanding the principle, there's no force. Now the car speeds up, accelerates. Now you feel a force. You're pushed back into your seat. Not because you're moving, but because your motion is changing. The force appears when velocity changes, not when velocity exists. This is profound. Motion itself requires nothing. No force, no energy input, no ongoing cause. Motion just is. It's change in motion that requires force. Okay, so why does this matter? Why am I spending so much time on this? Because it reveals something fundamental about the universe. Something Feynman kept coming back to in his lectures. The universe has no preferred state of motion. There's no such thing as at rest in an absolute sense. Think about that. Right now, you're sitting in a chair. You think you're at rest. But you're on Earth, which is spinning. So, you're moving at about 1,000 miles per hour, and Earth is orbiting the Sun. So you're moving at about 67,000 miles per hour, and the Sun is orbiting the center of the galaxy. So you're moving at about 500,000 miles per hour, and the galaxy is moving through space, so you're moving at over 1,000,000 miles per hour. At rest? You're not at rest. You're moving incredibly fast, but you don't feel it. You can't feel it, because motion itself doesn't cause any sensation. Only change in motion causes sensation. Here's Feynman's insight. There is no absolute motion. Only relative motion. Motion compared to something else. And all the laws of physics work exactly the same regardless of how fast you're moving. As long as you're moving at a constant velocity, not accelerating, everything behaves identically. This is the principle of relativity, not Einstein's relativity, not yet. This is Galilean relativity, the idea that motion is relative, not absolute. And it's at the core of understanding how the universe works. Let me give you an example Feynman loved. Imagine you're on a train, a perfectly smooth train, moving at constant velocity. You're inside a windowless car. Can you tell you're moving? Can you do any experiment inside the car that would reveal your motion? No, you can't. Drop a ball, it falls straight down. Throw a ball, it follows a parabola. Everything works exactly as it would if the train were stopped, because there's no physical difference between being at rest and moving at constant velocity. Now, the train speeds up, accelerates. Suddenly, you can tell. The ball you drop doesn't fall straight down anymore. It falls backward relative to the train. You feel a force pushing you back. Acceleration is detectable, constant velocity is not. This tells us something deep. The universe doesn't care about velocity, only acceleration. The laws of physics are indifferent to uniform motion, but they respond to changes in motion. Why? Why should the universe be built this way? Feynman would say, I don't know, and neither does anyone else. But that's how it is. That's what we measure. That's what nature does. Now, here's where it gets interesting, because if motion doesn't require a cause, if objects naturally continue moving, then what about things that are at rest? What's stopping them from moving? Nothing. They're not being stopped. They're just moving at zero velocity. And zero velocity is just as valid a state of motion as any other velocity. It's not special. It's not preferred. It's just one possibility among infinite possibilities. But wait. If zero velocity isn't special, why do things tend toward it in our experience? Why does everything eventually stop? Friction, interactions, energy dissipation. But these aren't fundamental. These are complications, details of how matter behaves in groups. At the fundamental level, particles don't tend toward rest. They tend toward nothing. They just keep doing whatever they were doing. Let me show you something Feynman pointed out. Something that blows people's minds. If you throw a ball straight up, it rises, stops, and falls back down. We say it stops at the top. But does it really? Think carefully. At the very top of its trajectory, the ball has zero velocity. For an instant, it's not moving. But is it at rest? No, because an instant later, it's moving again. Downward this time. So what's the difference between the ball at the top of its trajectory and a ball sitting on the ground? Both have zero velocity, but one is temporary. One is passing through zero on its way from positive to negative velocity. The other is stable. Feynman would ask, what makes one stable and the other not? And the answer is forces. The ball on the ground experiences an upward force from the ground, balancing the downward force of gravity. Zero net force, so the velocity stays zero. The ball at the top of its trajectory experiences only gravity. Net force downward. So the velocity changes. See the pattern? It's not about motion or rest. It's about whether forces are balanced or unbalanced. Balanced forces, velocity stays constant. Unbalanced forces, velocity changes. And at rest is just constant velocity equal to zero. Now let's talk about something else, because motion isn't just about objects moving through space. Motion is about energy, and energy is where the real mind-bending stuff happens. You probably learned that kinetic energy is the energy of motion. An object moving has energy. An object at rest has no kinetic energy. Simple. But wait, we just established that motion is relative. So kinetic energy must be relative too. An object moving relative to you has kinetic energy in your frame of reference. But relative to itself, it's at rest. Zero kinetic energy. How can energy be relative? How can the same object have different amounts of energy depending on who's measuring it? Feynman loved this question, because it reveals that energy isn't a substance. It's not a thing objects possess. It's a property of states. And states depend on your reference frame. Here's an example. You're standing still. A car drives past you at 60 miles per hour. The car has kinetic energy. Lots of it. Now, imagine you're in another car, also going 60 miles per hour. You look at the first car. It's not moving relative to you. Zero kinetic energy. Same car. Same moment. Different amounts of energy. How is this possible? Because energy is about relationships, not about objects in isolation. But here's the crucial part. Even though kinetic energy is relative, changes in kinetic energy are not. If the car speeds up, both you and the other driver measure the same change in energy. The car had to do work to accelerate. That work is absolute. Everyone agrees on it. This is a deep principle. Absolute quantities are related to changes, not to states. Velocity is relative. Acceleration is absolute. Energy is relative. Change in energy is absolute. Feynman emphasized this constantly. Physics isn't about states. It's about transitions, changes, processes. The universe doesn't care where you are or how fast you're going. It only cares about what changes. Now let me tell you about something Feynman discovered. Something that changed how we think about motion entirely. It's called the principle of least action, and it's one of the most beautiful ideas in all of physics. Here's the setup. An object moves from point A to point B. It could take many different paths. It could go straight. It could curve. It could loop around. Infinite possibilities. So, which path does it actually take? Newton would say, follow the forces. Calculate the acceleration at every moment. Integrate to get velocity. Integrate again to get position. And you'd get the right answer. But that's a lot of work. And it doesn't feel very fundamental. It's like the universe is doing calculus at every instant. Feynman showed a different way to think about it. Instead of asking how the object moves from moment to moment, ask which path, out of all possible paths, the object prefers. And the answer is the path that minimizes something called action. Action is a quantity defined for every possible path. It's a number, and nature chooses the path where this number is smallest. That's it. That's the rule. Minimize action. Now, what is action? It's related to energy, but it's not energy. It's energy multiplied by time. Or more precisely, it's the integral of the Lagrangian over time. But you don't need to know the details. The point is, it's a well-defined quantity. And nature always chooses the path that minimizes it. This is astonishing, because it means the object knows about the future. It doesn't just respond to forces in the present moment. It somehow samples all possible paths and picks the best one. Feynman spent years thinking about this. How can a particle know about future paths? How can it choose? And his answer, developed into what we now call quantum mechanics, is that it doesn't choose. It takes all paths simultaneously, and they interfere with each other, and the path of least action is the one that survives the interference. But that's quantum mechanics, and we'll get there. For now, the classical picture is enough. Motion isn't about forces pushing objects moment by moment. Motion is about objects optimizing over entire trajectories, choosing the path that minimizes action. This is a completely different way of thinking about physics. Not what pushes the object forward, but what path does the object prefer? And the math works out. It gives the same predictions as Newton's laws. But the conceptual framework is radically different. Feynman called this the variational principle, and he thought it was one of the deepest insights into how nature works. Not because it makes calculations easier, though sometimes it does, but because it reveals a kind of economy in nature, a preference for simplicity, for efficiency. Okay, let's shift gears, because I want to talk about something Feynman was obsessed with, something he thought most people completely misunderstood. Momentum. You probably learned that momentum is mass times velocity. P equals mv, and the reason momentum matters is conservation. In a closed system, total momentum never changes. True. But why? Why is momentum conserved? Your teacher probably said, because of Newton's third law. Every action has an equal and opposite reaction. Okay, but why? Why does nature obey Newton's third law? Feynman would push further. He'd say, conservation of momentum isn't a consequence of Newton's laws. It's deeper than Newton's laws. It's a fundamental symmetry of the universe. Here's what he meant. The universe looks the same everywhere. There's no special location in space, no preferred point. Space is homogeneous. And it turns out, mathematically, that homogeneity of space implies conservation of momentum. This is called Noether's theorem. Every symmetry of nature corresponds to a conservation law. Space is homogeneous, so momentum is conserved. Time is homogeneous, so energy is conserved. Space is isotropic, meaning there's no preferred direction, so angular momentum is conserved. This is profound. It means conservation laws aren't coincidences. They're not separate facts we discovered about nature. They're consequences of the structure of space and time. The universe is built in such a way that certain quantities must be conserved. Feynman loved this, because it connects abstract mathematics to physical reality. Symmetry isn't just a pretty pattern. It's a deep principle that constrains how the universe can behave. Let me give you an example. Imagine you're in space, far from any planets or stars. You're floating, at rest. You throw a ball. The ball moves forward. You move backward. Why? Conservation of momentum. Before you threw the ball, total momentum was 0. After you threw it, the ball has momentum in one direction, and you have momentum in the opposite direction. The total is still 0. Momentum is conserved. But why is it conserved? Because space is homogeneous. There's no difference between here and there. So, the laws of physics can't depend on position. And if the laws don't depend on position, then momentum must be conserved. See how deep this goes? It's not about forces. It's not about interactions. It's about the fundamental structure of reality. Space has no preferred location, so momentum cannot change on its own. Now, here's something Feynman pointed out that most people miss. Momentum is a vector. It has direction, and the direction matters just as much as the magnitude. Two objects, same mass, same speed, moving in opposite directions. Same momentum? No. Opposite momentum. They cancel. Total momentum, 0. This seems obvious, but think about what it means. The universe cares about direction. Not just how fast things are moving, but which way. And when objects interact, when they collide or exert forces on each other, the direction of momentum must be preserved just as carefully as the magnitude. Feynman used to say, "Nature keeps track of everything. Every component of momentum in every direction is accounted for. Nothing is lost, nothing is created, just rearranged." Let me tell you about one more thing, because this is where Feynman really shines. This is where his insight goes beyond textbooks and reveals something truly beautiful. Motion, at the quantum level, isn't what you think it is. An electron doesn't have a position and a velocity like a ball rolling down a hill. It doesn't follow a single path. It doesn't move in the classical sense at all. Feynman developed a way of thinking about quantum motion that's completely different from anything you learned in school. He called it the path integral formulation. And the idea is this: a particle doesn't take one path from A to B. It takes every possible path, all of them, simultaneously. Sounds crazy, right? How can something take every path? But that's exactly what happens. The particle exists in a superposition of all possible trajectories. Straight paths, curved paths, loops, zigzags, everything. And here's the kicker. Each path contributes to the final probability. Each path has an amplitude, a quantum number associated with it. And you add up all the amplitudes, accounting for their phases, their quantum interference, and you get the probability of the particle arriving at B. Most of the paths cancel out. Their amplitudes interfere destructively. But the paths near the classical path, the path of least action, interfere constructively. They add up, and that's why we see classical motion, not because the particle only takes that path, but because all the other paths cancel. Feynman showed that this picture, as bizarre as it sounds, reproduces all of quantum mechanics. It's mathematically equivalent to the standard formulation. But conceptually, it's completely different. And it reveals something profound. Motion isn't about objects moving through space. Motion is about probabilities propagating through space. The particle doesn't have a definite trajectory. It has a wave function, a spread of possibilities. And when you measure it, when you interact with it, the wave function collapses and you find it somewhere. Feynman used to say, "Nobody understands quantum mechanics." And he was right. We can calculate it, we can predict it, but the picture it paints of reality is so alien, so unlike our everyday experience, that we can't truly claim to understand it. But here's what we can say. Motion at the quantum level is fundamentally different from motion at the classical level. It's probabilistic, it's non-local, it's weird, and yet it's the foundation of everything. Atoms, molecules, chemistry, biology, consciousness, all of it emerges from quantum motion. So when you ask, what is motion? The answer depends on the scale. At the human scale, motion is objects changing position over time. At the fundamental scale, motion is amplitudes interfering, probabilities evolving, wave functions spreading through space, and Feynman understood this better than almost anyone. He could move between the classical and quantum pictures effortlessly. He could see the connections. He could translate the math into physical insight. Let me bring this all together, because we've covered a lot, and I want the big picture to be clear. Motion doesn't require a cause. Objects in motion stay in motion, not because something is keeping them moving, but because there's no reason for them to stop. The default state of matter is uniform motion. Change requires force. Motion itself is free. There is no absolute motion, only relative motion. You're never truly at rest. You're always moving relative to something. And the laws of physics don't care how fast you're going, only whether you're accelerating. Force doesn't cause motion. Force causes change in motion, acceleration. And acceleration is absolute. Everyone agrees on it. But velocity is relative. Everyone measures it differently. Energy is relative. Kinetic energy depends on your reference frame. But changes in energy are absolute. Work done is the same for everyone. Momentum is conserved because space is homogeneous. There's no preferred location. And this symmetry, this uniformity, constrains the laws of physics. Conservation isn't a coincidence. It's a necessity. At the quantum level, motion is probabilistic. Particles don't have definite trajectories. They take all paths. And the classical world emerges from the interference of quantum amplitudes. This is what Feynman understood. This is what he tried to teach. Motion isn't simple. It's not just objects changing position. It's a window into the deepest structure of reality. Symmetry, conservation, relativity, quantum superposition. And here's the beautiful part. We figured this out. Creatures made of atoms, living on a tiny planet, evolved to throw spears and find fruit. We developed mathematics sophisticated enough to describe the motion of everything from electrons to galaxies. We can't see quantum superposition directly. We can't feel relativistic effects in our daily lives. But we deduced them. We tested them. We built technologies based on them. GPS satellites account for relativity. Computer chips rely on quantum mechanics. The theories work. Feynman used to say, physics is like sex. Sure, it may give some practical results, but that's not why we do it. And he was right. We study motion not because it's useful, though it is. We study it because we want to understand. We want to know how the universe works, at the deepest level. And motion, simple motion, an object changing position, leads us to the most profound insights. Relativity, quantum mechanics, symmetry principles, conservation laws, the structure of space and time itself. So you've been lied to about motion, not maliciously, not intentionally. But the story you were told in school, the story of forces causing motion, of objects at rest being natural, of velocity being absolute, that story is wrong. The truth is stranger, more beautiful, more elegant. Motion is the default. Rest is relative. Forces change motion, they don't create it. And at the quantum level, motion isn't even well defined until you measure it. Feynman spent his life exploring these ideas, teaching them, refining them. And what he showed us is that the universe is far more subtle than it appears. That common sense is often wrong. That intuition developed for survival on Earth doesn't apply to the cosmos. But we're not limited by our intuition. We have mathematics, we have experiments, we have the scientific method, and through these tools we can see past the lies, past the misconceptions, and glimpse the actual structure of reality. That's the power of physics. Not memorizing formulas, not solving problems, understanding, really understanding, seeing the world as it actually is, not as it appears to be. And motion, fundamental motion, is where it all begins. Every object, every particle, every wave in the quantum field, they're all moving. Always, never truly at rest. Never truly isolated. Part of a vast, interconnected, dynamic universe. Feynman saw this, he understood it, and he tried, through his lectures, his books, his diagrams, to help us see it too. To help us understand that motion isn't what we think it is, that the universe is stranger and more wonderful than we imagine. So, the next time you throw a ball, watch it arc through the air. Remember, it's not being pulled down by gravity in the way you think. It's following a geodesic through curved space-time. It's not slowing down because motion naturally decays. It's being stopped by countless molecular collisions. And at the quantum level, it's not even taking a single path. It's existing in a superposition of all possible trajectories. That's motion. That's reality. That's what Feynman taught us, and it's beautiful. genuinely, profoundly beautiful, that we can understand this, that we can see past our evolved intuitions and grasp the actual laws governing the cosmos. You've been lied to. But now you know the truth. Motion is the natural state. Change requires force. Velocity is relative. Energy is relative. But conservation is absolute. Symmetry is fundamental. And quantum mechanics is the foundation of it all. This is physics. This is how the universe works. Not the simplified version, not the intuitive version, the actual version, the true version, the version Feynman dedicated his life to understanding and explaining. And now you know it too. You can't unknow it. You can't go back to the simple story. You've seen behind the curtain. You've glimpsed the machinery. And it's more elegant, more sophisticated, more beautiful than you ever imagined. That's what Feynman gave us. Not just knowledge, not just formulas, understanding. Deep, profound understanding of how motion actually works, and that's a gift worth having, worth cherishing, worth passing on, because the truth about motion is the truth about everything. Space, time, matter, energy. It's all connected. It's all unified by the same principles, the same symmetries, the same mathematical structures. We are the universe understanding itself. Atoms arranged in such a way that they can contemplate atoms, motion studying motion. And in that contemplation, in that study, we find meaning. We find beauty. We find truth. Feynman knew this. He lived it. And he tried to share it with everyone who would listen. Not everyone understood. Not everyone cared. But for those who did, for those who saw what he was showing us, it changed everything. So you've been lied to about motion, but now you know better. And that knowledge, that understanding, is yours forever. Use it. Think about it. Let it change how you see the world, because once you truly understand motion, you understand the universe. And that's not just physics, that's philosophy, that's poetry, that's the deepest kind of knowledge there is. Motion is everything, and everything is motion. Feynman showed us that, and we should never forget it.